Welcome to Chapter 13, Part 2, and the title of this lecture is What Do All These Numbers Mean? First thing I want to tell everybody is you're not required to memorize the formulas. Chapter 13 is filled with many different formulas for calculating different numbers, different values. In my class, the focus is on understanding conceptually and in being able to interpret what the numbers mean, not remembering or memorizing the formulas to get the numbers, to get these particular values we're going to talk about. We're going to use and rely on the TI-8384 calculator to do those computations. So let's just review for a moment here the idea of the statistical hypothesis when we're doing linear regression. Get my pen going. Okay, so the null hypothesis is always going to be no linear relationship between the variables. And, well, I'll just leave it at that, variables. I was going to say x and y, and I'll just put that up here parenthetically, or y and x. Y and x are the conventional letters that we do use to represent the independent, and the dependent is y, the independent, which is x. But we certainly don't have to use those particular letters. So the alternate, or the theory here, is going to be that there is a linear relationship between the variables. So this first set of null and alternative hypotheses that I'm writing down are written in words, okay? And so now we want to translate to math, because again, the engine behind statistics is mathematics. To math, not to make, what am I saying? To math. So we want to translate these to math. Now, the other thing, as we move into this translation, the other thing I want to make a point about is the idea that we have statistics, which in this case is going to be b from the equation y hat equal bx plus a. This is going to come from the data. And we're going to have parameters. And in this case, the parameter is beta. And this is going to, again, parameters come from the population. And the parameter is going to be part of the equation y equal beta x plus alpha. Now, students are understandably confused about having two different versions of the equation here. But the thing you have to remember is that this equation on the right, this one, is theoretical. And in a sense, I'm actually going to go so far as to say hypothetical. Because in almost every case, we believe this equation exists. In other words, if we could sample every member of a population, which could have millions and millions or billions of elements, okay, in that set, making it impossible in many cases to sample the entire population. Therefore, this equation we can almost think of as being hypothetical. It's out there, we believe it's out there, but we have no way of measuring these parameter values, beta and alpha specifically. But on the other side here, we have data, and the fact that we've actually physically sampled the data, we could think of this equation as tangible in the sense that I can actually calculate beta. So, I'm sorry, not beta. I can actually calculate B. Beta, it's out there, we believe it exists, but unless I can sample every member of the population, I don't have any way of calculating beta. B, we can always calculate. Now, the idea though is when we're talking about the hypothesis up here, this hypothesis is about the population, okay? So this hypothesis is a hypothesis about the population, not about the data. This is about, the hypothesis is always about the population, okay? Therefore, when we create our statistical hypothesis, it's going to be in terms of beta. So the null hypothesis that we wrote above, no linear relationship, that's equivalent mathematically to saying beta is equal to 0. Alternatively, we could say beta is not equal to 0. And there's 3 ways to say beta is not equal to 0. Beta is greater than 0. Beta is less than 0. Or beta is not equal to 0. So we'll use the H1 or the alternate beta greater than 0 when our theory is, or when we believe that the relationship is linear and positive. We'll use this less than when our theory is, okay, so the greater than is going with the positive. So we'll use the less than in the alternate when we believe that the relationship is linear and negative. And we'll use not equal to when we have no clue. Not used often in linear regression. Because when we look at the scatter plot, we should have some idea about whether there's a positive association or a negative association. Mathematically, theoretically, there are 3 options for the alternate: greater than, less than, or not equal to. But by far, greater than or less than are used most often. Now, where does the p-value come into all of this? Well, the idea here goes like this. So here's the question we're going to ask. Is B from the data significantly different from 0? Because in the null, we're assuming no linear relationship. And in the alternate, they're going to say that it's a positive or a negative association, or a positive or negative linear relationship. So the question is going to be, in a different way, we could say how rare and unusual is B, that's coming from the data, assuming H naught is true. So the idea here is that if H naught is true, that's supposed to say true. If H naught is true, I'm not even spelling that right, true. If H naught is true, then beta or B should be 0. That's what we expect. If H naught is true, we expect B to be 0. Now, if B is significantly different than 0, then our p-value will be small. The smaller the p-value, the more significant the data. The smaller the p-value, the stronger the evidence against the null hypothesis. In a nutshell, if p is small enough, and we say small enough when it's at least alpha, the significance level, then we reject H naught, we reject the null. Or if p is greater than alpha, we do not reject the null. Oops, needed an H naught over here. Okay, so I'm out of space on this page, I would say. Now, so one of the numbers we're going to look at in our statistical analysis, well, the first thing we're going to do is set up the hypothesis. The next thing we're going to look at is the p-value. If the p-value is really small, we'll reject the null hypothesis. We'll have evidence of a statistically significant linear relationship, either positive or negative, depending on how our alternator or what our theory is. And then we'll go on to the next part of the linear regression analysis. Now, there are several different numbers that we look at. And a lot of times I think about regression analysis like putting together the pieces of a puzzle. When all the pieces fit together, then we say we have a good model and we have an appropriate model. One of the other pieces of the puzzle is this thing that we call the correlation coefficient, R. And R measures the strength of the linear relationship between two quantitative variables. And it describes the direction of the linear association, and it indicates how closely the points in a scatter plot are to the least squares regression line. Now, that's a lot of information. Let's go through this point by point. Now, R is always a number between -1 and 1. And when R is equal to either -1 or 1, then we say we have a perfect correlation, either a positive or negative. The sign of the correlation tells us the direction of the association. So if we have a negative R value, it means we have a negative linear relationship. If we have a positive R value, it means we have a positive linear relationship. The magnitude of the correlation coefficient, or its absolute value, indicates the strength of the linear association. If the data follow a straight line, R is 1 or -1. And that means if we have an R value that's exactly 1 or exactly -1, that's a perfect linear association. That really never happens, but theoretically that's what it would mean. And the correlation coefficient only measures the strength of the linear association. We have to look at the scatter plot to determine the type of association that's present. And then the other thing about the correlation coefficient is that it's using these things, the standard score concept that we talked about earlier, and it has no units. So we look at R in terms of its sign and its magnitude. So let's look at it. Let me draw a couple of hypothetical pictures here. So if we have an R value that's exactly equal to 1, okay, what that tells us when we look at a scatter plot, okay, and I'm not going to put, this particular scatter plot's not going to have units and stuff like that. I just want to make the point here of what these different R values mean. So if R is exactly 1, the line is going to have a positive slope, and every data point, every observation will be exactly on the line. That's a perfect positive linear correlation. And on the other hand, if R is exactly equal to -1, put a Y here too, then the slope of the line will be negative. Okay, so this is when R is equal to -1. And again, every single point will be on the line. So the other extreme would be r equal to 0. And r equal to 0 means there is no linear correlation. So this would be, again, the shotgun scattering of these points where there's no trend upward or downward. So therefore, and the other way to think about it is, there is no line that's going to fit this data very well at all. So this is perfect positive. This is perfect negative. And this is perfect no association. Now, these things really never happen. And so what we end up with is something more realistic, which is, and so why do I say those two, upper three, never happen? Well, the first two, the r equal 1, r equal -1, exactly, they never happen because in the real world, we always have this thing called variation. And what it means is that if we have, say we have a relationship, or say our p-value is indicating that we have a significant positive relationship, well, what's going to inevitably happen is that those points aren't going to be exactly on a line. They're going to vary somewhat around that line. And what that means is that r is going to be less than 1, because it's not a perfect linear correlation, but it will be greater than 0 because it's a positive linear relationship. And then the other practical situation that we fall into is the situation where the relationship between the variables is a negative relationship. And again, the points don't fall exactly on the line. They have some there's variability, and the points are scattered around the line somewhat. And this situation is going to happen when r is not exactly or not equal to -1, but it's less than 0. So this would be positive with variation. This would be negative with variation. And these, again, are the ones that we see in the real world. I mean, if you don't see systems in the real world where there's no variation. It's just, we could invent situations, the human mind can invent situations where there's no variation, but in nature, in the real world, when we're dealing with reality, that there will be variability. Okay, so R is a statistic. R comes from data. R will be something we calculate. Just like with B and beta, there's a corresponding parameter that we call rho. And we can actually also look at another form of the statistical hypothesis in this case. So when we were talking about the null from earlier, or when I was describing the null earlier, I talked about the slope of the regression line, and beta is the population slope. And remember that assumption of no linear relationship, when we talked about that scatter plot, that was the shotgun scatter plot. Okay, that was the situation where the line that fit the data the best theoretically would be a horizontal line. But notice that notice that that same scatter plot that would indicate a horizontal line for the best fit line also corresponds to the data set where there's no linear relationship. So it turns out that beta equals 0, 0 or rho equals 0 are equivalent null hypotheses. And also similarly for the alternate, okay, then we could also describe the alternates in the same way. Okay, so I guess I'll make a notation here. These are the null hypotheses, the way I'm writing this out. I'll just kind of, whoops, I'm trying to make a dash line here. And then the alternate possibilities would look like this. So in the alternate for beta, we had beta greater than 0, or we had beta less than 0, or we had beta not equal to 0. And notice each of these can also be looked at in terms of rho instead of beta. So the alternate here could be rho greater than 0, rho less than 0, or rho not equal to 0. And again, if you recall the output we looked at on the TI earlier, the hypothesis test the TI does is in terms of both beta and rho. And the two hypothesis tests are equivalent to each other. Depends on your point of view. I like to look at, I like to look at the slope because the slope is the rate of change of the variables. And I think that in terms of explaining what, in detail, what the relationship means, having the rate of change increasing or decreasing as in terms of significance is something that gives us more to discuss and interpret and explain. And that's one of the reasons I like to focus on beta, the slope of the line. Okay, now there's another number that we should consider, which is r squared. And r squared is the correlation coefficient squared. In other words, r squared is r squared. In any case, let's talk about this. So r squared is called the coefficient of determination. And it's defined to be the sum of the square total minus the sum of the square error over the sum of square totals, which is sum of square residual over the sum of square total. So since the denominator is the total, is a total, it makes the ratio a percent or a proportion. This r squared value is extremely useful in statistics. It's got a more of an interpretive value than r, because we can say r squared is a measure of the proportion of the total variation explained by the linear relationship. Okay, and this is a confusing idea. Let me go to the example we were talking about earlier and try to explain this and make sense of this. So here was the question from before. Okay, the question here was, can we predict or maybe I should say, how can we predict, let me insert how can we predict the height HEI, the height of a man's future partner? That was sort of the idea. That was the idea. Okay, now, when the first time I described this example, I came at it from the point of view of, let's find the best fit line, let's see if we have a significant relationship, et cetera, et cetera. But I want to look at it in a different way. Suppose, for a moment, suppose we didn't have the husband's heights. Okay, and so then we only had the wife data. Okay, so we're going to look at this in a univariate case before. Well, typical would be how we would estimate or how we would predict the height of a randomly selected person from the set of women heights. And so our prediction here would just be the average height of the wives. And so in a sense, or what I want to do here, I'm going to guess where this line goes. Okay, but in one way we can think about this is in terms of competing hypotheses. All right. So let me see if I can explain this. So if I didn't have the husband variable, or if I found the husband variable was not significantly related to the wife variable, then what we would end up with in our linear regression analysis, of course, would be a horizontal line, and that would be the line y equal w bar, okay? The average height of the wives. And the question is, another way to think about this hypothesis is H naught, okay, is beta equals 0. That's that horizontal line. H1 in this case is beta greater than 0. Okay, so this is equal 0. This is greater than 0. So if P is less than our specified alpha, say, we're going to reject the null and we're going to say we have a significant relationship, and we're going to use the yellow line for our predictions. Okay. Now, when we are looking at this as a single variable, just the wife data, then we need two measures. One measure is the typical, and then we also, remember, needed this measure of spread, okay? And this measure of spread, when we were in Chapter 5, was the standard deviation. But in regression analysis, we don't bother with the standard deviation, because we aren't going to get a number to interpret. We're actually going to do a comparison between between the two possible models, the horizontal line and the slanted line, or the line with the positive slope. So let me see if I can explain this, okay? So if we're looking at it in terms of a univariate situation, one variable, then what we're going to do is we're going to look at, let me pick a color here. Well, let me go with blue. Let's just go with black. All right. Now, okay, so let me explain this. So let me pick a point. I'm going to just pick this point right here, okay? And I want you to notice something about this point. First of all, I want you to recognize that this point has coordinates. I'm going to call them x1 and y1, but x1 and y1 are numbers. And I can estimate those numbers. So like, for example, x1 here, let's estimate it. It's about, say, I'm going to call it 86. And then y1 here, that's, looks like it's just about 180. But I use subscripts when I want to generalize and talk about fixed numbers or constants that don't necessarily have that, and think about them in the abstract, in the sense that they're not concrete numbers, they're hypothetical numbers, say, or whatever. But in any case, the point here is that the observed value, the data point, has two coordinates, x1 and y1. And now if I project down to the x-axis, okay, I want to point out that there are two other ordered pairs to consider. There's the ordered pair x1 w bar, because remember, every point on that horizontal line is a w bar, it has w bar height. And then there's a point here on the line. And so all three of these points have the same x value because they line up vertically. but each one has a different y value. So this one I'm going to put a hat on. That's the predicted value corresponding, and I'm putting a subscript of 1 because it's the predicted value that corresponds to x sub 1. Okay, so here is where the rubber meets the road on this. If the null is true, then my measure of spread is going to be reflected by this total distance, okay? So if the null cannot be rejected, then we're stuck. Then the best thing to do would be to use the average of the women's heights and to consider the deviations in terms of distance from y bar, or from w bar is what I'm calling it here, up to the actual observed value. So the deviation is going to be the y value minus y, and I like to write y bar here because really the w, and let me just also call it y bar. I'll just change it to y bar to be consistent with my y notation. But because, and again, y bar won't have, actually, you know what, I don't want to do that. Let me just stick with w bar. That's fine, w bar. So it won't be the same as the formula in the book. That's what I'm concerned about. But maybe I'll do it both ways. I'll do w bar because I want you to really see that w bar is the average of the women's heights. So if I take, now first of all, I'm looking at this first deviation. The first deviation is just the observed value minus w bar. That's the total deviation from the average up to the actual observed value. And again, if you remember when we were calculating the standard deviation, one of the things that we would do is we would take those deviations, we would square them, and then we would sum those all up. And then, of course, if we're talking about the standard deviation, we divide this by n minus 1 and then take the square root. But see, in regression analysis, we want to compare the spread based on the univariate case, or the failure to reject the null, to the spread if we have this significant linear relationship. This quantity right here, this is SST. This is the sum of squares total. So the idea here is if I took every one of these points in the data set and did calculated the deviation between its y value and the average of the women's heights, squared them all, add them all up, I'd have the sum of square total. So this represents total variation in y, in the y variable, okay? But then we have a second part. We have the option, the p-value is small, we reject h naught, and then the question is, how much variation is left over? Leftover, stuff that's left over is called residual. So if we're able to reject the null, we have a small p-value, so we reject the null. Next question is, how much variation is left over? What's the residual variation? So when I go back up here and look at my example I'm talking about, then what we end up with is each one of these points is going to have two components now to its variation. This component, leftover, this is the residual. Okay, this distance from the point down to the best fit line is the residual. And then the distance from the point down to the average, this is the explained. Because by deciding to go with, in a way, maybe, it's not necessarily a rotation, but by deciding to, rather than use the horizontal line, by being able to reject the null, then what we're really doing in a sense is we're saying, no, we're going to rotate this line up and we're going to use the best fit line for our predictions. Therefore, the distance from the predicted value off the best fit line down to the average line, that's explained variation now. And the only variation that we have to consider in our model is this residual or leftover variation. Now, every single point in this data set is going to have the same kind of a breakdown. And so if I take the sum of each y hat value, oops, I'm sorry, I did that wrong. Let me start over. If I take the sum of each observed value for y and subtract its corresponding y hat value, square all of those, sum them all up, this is the sum of square E for error. Now, in statistics, we end up with terms that have different words that really have the same meaning. The residual or leftover variation sometimes is also called the error in the model. Okay, the error in the model. So, how do these things break down? Well, if I take the sum of square errors divided by the total variation we had to start with, this is the proportion of unexplained variation or error and if in using the complement rule, okay, since there are only two kinds of error now, we broke it into two parts. Part one is what we just talked about, the leftover or residual error. And then part two is the explained error. So if we take now, since there's two types of error now, if we take the sum of square error over total and subtract SST for sum of square total and subtract that from 1, what we have is the proportion of explained error. And this is R squared. This is what we call R squared.